Well, thank you very much for organizing the conference. Right, since as the first speaker, I need to thank the organizers. So I want to talk about differential geometry. On C-infinity ring spaces. And the question is, I guess going back to that paper that Ray and I wrote years ago, is can we make sense of differential geometry on singular spaces? And my understanding that the answer is yes and no. And so why yes? Because there are lots of frameworks. Maybe too many, right? So for example, so this is going back to 1960s. So there are differential spaces. That's Sikorsky. And people have been working on them for, I don't know, since 1970s. There are diffeological spaces. That's KT Chen and independently Surreal. And I can't remember how to spell it. If my handwriting is terrible, you can't tell that I'm misspelling it. Right? I'm kind of proud that KT Chen is from Urbana. So, but he's no longer there. And then you see infinity schemes, which are less well known. That's the book, 1980. And derived manifolds. That's Spivak, 2007. And I guess there is derived differential geometry. And maybe Ping Shu will explain it to us. But mostly inaccessible to me. My quasi-categories are not very good. If anybody can explain them to me, I'll be very happy. So why no? Oh, and I should probably mention the D-manifolds and D-stacks by Joyce. Right, so why no? So I'd like to have things that you can find in a textbook in differential geometry. I want to have vector fields flows. I want to integrate the vector fields to flows. Differential forms. Stokes. Cartan calculus. So I don't know the literature very well. It could be that some people have written it out, but I haven't seen it and I couldn't find it. And so I want to start with differential spaces. Right, there are all these choices, but to me, the theological spaces seem like not a very good place to start if you want flows. If you want to have vector fields or you want to have flows, there is a preprint by Bloman, which was posted yesterday, I think, where he lays out a program to have Cartan calculus on a class of the theological spaces. So I had to adjust my talk to mention it. But I don't think people know how to integrate vector fields on the theological spaces. So I was working, so I want to start with this. And right, there's literature on C-infinity schemes. There is, the book invented them as a framework for synthetic differential geometry. But again, my understanding of synthetic differential geometry is not very good, but I couldn't figure out how they integrate vector fields in synthetic differential geometry. I think it's all infinitesimal. But these things will show up soon. This is quasi-categories. These are homotopy sheaves of simplicial C-infinity rings. And if that doesn't intimidate you, I'm very proud of you. Intimidates me. All right, so let's start with the definition. So a differential space is a set, a collection of functions, real valued, such. So once you choose functions on a set, so give M the initial topology. So smallest topology such that any f in script f is continuous. And then there are two strange conditions that you impose for any n bigger than 0, for any collection of functions in this script f, for any smooth function in C-infinity Rn. Well, you can compose H and with this tuple, right? If I take n functions on a set, they take values in Rn. I can think of it as a Rn valued function. I compose it with H, and I want it to be back in F. And the second condition is given if a function is locally in F, then it's in F. And that just says that for any G from M to R, given G from M to R and a point such that for any point in M, there exists a neighborhood U of X and F in script F, so F depends on X such that G restricted to U is F restricted to U. This implies that G is an F. So I don't know how many people have seen this. To me, this looks weird. But let me give you an example. So let's take M to be second countable Hausdorff manifold. And let's take script F to be smooth functions. So I'm going to give, so the manifold comes with a topology. Then claim is then M is a differential space. And I guess conditions 1 and 2 are fairly easy to check. The one thing that may be not completely obvious is that the topology is initial, but it is. And since I don't have a lot of time, people told me not to go over by more than half an hour. I'll skip the verification.
What goes wrong with not?
I don't think you'll get the initial topology. I mean, the topology and the manifold will not agree. I just wanted to make sure that this works. Here's another example. Let's take M in Rn closed. Let's take F to be smooth functions on Rn restricted to M. So this is really C infinity Rn mod ideal of functions that vanish on them. This is a differential space. And here's an example. Differential spaces are sort of like topological spaces. They're very general. So here's an example just to compare. Let's take X to be Hausdorff completely regular. Topological space. Again, I'm making my life easier, so I'm making these assumptions. You probably don't need it. And you can take F to be continuous functions. It's that crazy. This is a differential space. Right, I want to make 2 comments on this definition and why I find it weird. So condition 2 seems to say the following. Consider the sheaf C0 sub m of continuous functions on M. Right, once you give M a topology, you can look at all continuous functions. So let C infinity sub m be the subsheaf of C0m generated by F. I think I can do that. And then the condition, this sheafy condition seemed to me saying this. If I look at the global sections of this subsheaf, I just get F back. So it's sort of a ghost of a condition of that there is a sheaf of functions. One says that F is a C infinity ring. So here is a informal definition. The formal definition, when you see it the first time, makes no sense. So I'll just try to tell you what it's supposed to do, as opposed to what it is. So a C infinity ring is a set, let's call it script A, together with an infinite collection set of n-ary operations. So n greater or equal than 0. So think of it as some sort of a universal algebra kind of thing. It is. And I want one operation f subscript a from a to the n to a for any n, for any f, a smooth function. I guess I should have called it h to agree with the things I was doing earlier in C infinity Rn. So this probably does look weird to you. So compare, and then there is an associativity condition that you have a bunch of operations, you stick them together, and you can compose functions, the two notions match. So compare a commutative ring is a set R with countably many n-ary operations. Let's call it one. So let's call it P sub R. It will go from R to the N. So this is for all N. And we'll go from R to R, Rn to R. And P should be a polynomial with integral coefficients. Right? I can define commutative rings this way. Nobody ever does. But it's equivalent. Is this okay? All right. So I just erased the C infinity schemes, but you can imagine that once you have something like a ring, you could try to imitate what's been done in algebraic geometry. So in particular, there is a notion of a infinity ring space. And if you've done some graded geometry or supergeometry, you probably have dealt with ring spaces, or I don't know. I'm not sure. I don't know my audience, so I'm not sure which intuition I can appeal to. So what would it be? See Joyce. He has a book on it. So it's space plus sheaf of C infinity rings and such that stalks are local. I guess I should say a local C infinity ring space. So there is a notion of a ring being local, C infinity ring being local. There exists a unique maximal ideal. There's a subtlety in defining local C infinity rings, and I'm going to sweep it under the rug. You're not taking just arbitrary maximal ideals. You're sort of looking at things. You're looking at things called R points, right? So so they form a category. Joyce calls them LC infinity RS, local C infinity ring spaces. Right. So here is a proposition that I think hasn't been proven yet because nobody wanted to. There is a fully faithful embedding differential spaces. So Sikorsky differential spaces, you can shove them into local C infinity ring spaces. So you can have a different definition. And I wasn't going to do this, but I think I will. Okay, there is a global sections functor. The global section functor. Right, because if I have a ring space, I could just look at the global sections of the sheaf, and it's going to give me a C infinity ring. And so what the book proved is that there's a functor going the other way, spec. So I get confused about adjoints. It's the right adjoint to the global section functor. So sorry, this is op. It's a contravariant functor. Spec and goes from C infinity ring up to local ring spaces. So the essential image of the functor is C infinity scheme. So here I defined it for you. Well, actually, I told you nothing because I haven't told you how to do this. The nice thing is that once you know it's a right adjoint, it really doesn't matter how you construct it. And I could not make sense of the book's construction. It's very terse. And he appeals to topos theory, which I don't know. And one of the many things I don't know. But Joyce has basically took open Hartshorne and copied it. And it works. There are subtleties here because this functor is nowhere near as nice as the functor for commutative rings. So in particular, it's not injective on objects. Different rings could give you, very different rings can give you the same locally ring space. So this is why the book restricts, so the class of C infinity rings is huge. So the book restricts it to something more manageable to make this functor better behaved. So he has a nice class of C infinity schemes, and then you could do synthetic differential geometry over them if you want to. Wait. There is another piece of mathematics from the 80s I want to mention. C-infinity rings have a version of Caylor differentials. Or the analog of Caylor differentials. So this is 1984. This is Dubuc and Koch. Actually, their theorem is more general than C-infinity rings. They work with something called Fermat theories. You know how mathematicians are. If you can do something, you could make it more general so nobody could understand what you're doing. And that's what they do. No. Right, so the point is, for any C-infinity ring, there is a module. There is a notion of a module over a ring. And you can talk about derivations with values in the module. And there exists a universal derivation for C-infinity rings. So that looks like abstract nonsense. But note, if okay, if M is a manifold, A is smooth functions. So again, my manifold is a second countable in Hausdorff, just to keep the pathology out. Then this module of Caylor differentials is the Rahm differential forms. If you ever try to do Caylor differentials right, you can look at smooth functions in a manifold, and you can think of them as R algebra or commutative ring, and you can take Caylor differentials, and it's not going to give you differential forms. It's too big. So I get a little frustrated. People have been trying to do differential geometry in terms of commutative algebra, and I think no, there is no Caylor structure. So there is a notion of something in commutative algebra called Caylor differentials. Probably the same Caylor. Yeah, they exist for any commutative ring. It's algebraic geometry's way of saying differential one forms. If somebody hands you a commutative ring, they could ask you, what are the one forms? And they're Caylor differentials. They're called Caylor differentials. So okay, so this is kind of a nice fact, not entirely obvious. If you look at Joyce's book, he just says it's true, and he's not wrong.
So you're saying this is true if you do these guys, if you're starting with this infinity ring,
Yes.
it's not true if you repeat the same definition and start with the algebra?
Yes. Yeah, that's exactly the point. And the notion of a derivation is not the R algebra derivation. So C-infinity rings know about smooth functions, kind of. So derivations know about the chain rule. C-infinity ring derivations know about chain rule. And it's part of the definition. We're kind of used to the fact that if you look at the derivations from smooth functions to smooth functions, they are differential operators in the normal sense, but it's a theorem. There are situations where R algebra derivations are not C-infinity ring derivations. So once you have Caylor differentials, these are one forms. So your impulse should be, I think, is to take the exterior algebra of this module and get a de Rham complex. And for some reason, people haven't done it. So I've done it. So given a C infinity ring, the universal derivation extends to a degree 1 graded derivation on the exterior algebra. Right, so you kind of wonder where is the hard work? Why is there any hard work at all? The point is that this is a module over A, but it's not a free module. So there are relations between generators. It's generated by things that look like, it's generated by exact forms, but there are relations between them. And so you have to worry about how do you extend it when you have relations.
You say exterior algebra, you mean exterior algebra as an A module?
As an A module. Right, so one of the many things I'm sweeping under the rug is what's the notion of a module over a C infinity ring? It turns out that the reasonable definition is a module over underlying R algebra. So any C infinity ring is an R algebra. And there's evidence that this is a good definition. If you like category theory, there are back modules. So there's a more general notion of a module in category theory. You can define modules in arbitrary categories, or reasonable categories, and that's one of them. It happens to work. There are situations where back modules are not the right thing, but in this case, it's fine, right? So in other words, we get a C infinity algebraic de Rham complex. And the proof is basically, well, you go to the stack project and you see how algebraic geometries do it, and then you figure out what you need to change, and it seems to work. Right, so I mentioned the C infinity derivations, so maybe I'll give a definition. My notes tell me to give you the definition. Of a C infinity ring A is a map from A to A such that for any n, for any smooth function, for any n elements in A, x, remember we have an operation corresponding to f, and the condition you write down is this one. So I can take partials, and they define more operations. So take those, apply them to the elements, and multiplying by xi. xai. So this is sum over I. Sorry about the typos. And then you can replace derivations with values in the C infinity ring with derivations with values in the module. And that's what that guy is. So there are sort of two notions of derivations floating around, right? There is a derivation with respect to the wedge product here. That's what this D is. And then there is derivation in the C infinity ring spans. And wait. There exists a unique contraction map. So I'm going towards Cartan calculus. So if you want to have a Cartan calculus in a manifold, right, you should have differential forms, vector fields, contractions, Lie derivatives, and the relations between them that you can package in different ways. You can package them using super algebras, super Lie algebras, or a pair of two representations of a Lie algebra. But you want contractions. So there's a contraction to degree -1 derivations of the exterior algebra. It's unique once you use the fact that this is a universal derivation. There is a normalization. Right, and then you can define Lie derivatives. So they should go to degree 0 derivations by, well, you have contractions, you have the exterior derivative. So you could just do this. And one gets the whole Cartan calculus. But this is just for rings and for C infinity rings. So if you're differential geometry, you feel like you're done because that's what we do with manifolds. But if you're thinking this way, you're just getting started because you have to move everything to sheaves. And I don't really know sheaves well enough to do it easily, so I've been struggling with it. But I think I got it. It's famous last words, right? I think I have the proof. But I haven't. Yeah, I have a 20-page outline typed in, but I think some details need to be filled in. What else one could do? So I told you about this complex. You can, since you have if you have a C infinity ring space, including differential spaces, you can apply this. This is natural in the ring. That's what I should have said. So this construction of de Rham complex is natural in the ring. So you actually get a pre-sheaf of commutative differential graded algebras on any C infinity ring space, but it's not a sheaf. And Ray told me to sheafify it. So I did, which required work because I also wanted, so then you get differential forms. So the procedure is you do this to a sheaf, you get a pre-sheaf, and then you have to sheafify, and then you discover that things are a little weird because I don't know how many people worked with graded differential geometry, maybe a couple, maybe more. There's this subtlety in graded differential geometry that, or in graded geometry that with direct sums, right? So here's a annoying fact. If I have a collection of, let's take non-negative is a collection of sheaves of algebras or R algebras. And if I define the direct sum on some space, and if I define direct sum on an open set by just taking the direct sum of these guys, then this direct sum is not a sheaf, need not be a sheaf. So it seems like the right thing to do is not take direct sums. Somehow in graded geometry, this hasn't been noticed much because if you're dealing with free sheaves, or the sheaves are really sections of vector bundles, that issue doesn't show up. Well, even then it shows up. So when I was writing this complex, I put the dot there. I'm not taking the direct sum. I'm thinking of it as a sequence of modules. So here's an example. I have like 7 minutes. My note says you're on your own. So let's take the amount. It doesn't work for differential forms. So let's take M to be disjoint union of open balls of dimension n, say, so Bn1 and Rn standard open ball. And let's take a volume form. And they're disjoint. So if it were, if you were to look at these guys, right, it's unbounded because my dimensions are unbounded. And these are local sections, right? This is an open cover. On every element of an open cover, I have a differential form. The compatibility condition is vacuous. So I should have, so we get this sequence sitting in there, but it's not in the direct sum.
What if you did direct
And that would probably also be a wrong thing to do. But so people in graded geometry are sort of becoming aware of this. And I think there is a paper coming out this year. There's a guy in the Czech Republic whose name I forget, but maybe Ping remembers, who wrote this 80-page manuscript trying to fix issues in graded geometry around this. Right. What else can I tell you about the things I've been doing? There are two things I want to say. Right, I didn't emphasize flows in this talk, but Yale and I have been arguing about flows for the last 2 years. And in fact, we had some version of a paper. We have a version of the paper written maybe 1.5 years ago. So here is the infinity ring spaces. Differential spaces are like this, and C infinity schemes are like this. And in fact, C infinity schemes are much bigger than differential spaces, but the two theories just don't match. And if you start thinking of differential spaces as C infinity schemes, you discover that there's something funny about the definition of a differential space if you're looking at it from this point of view. And why do you have to have a set? You could just start with a C infinity ring. And then any C infinity ring will have a set of points as in algebraic geometry. It turns out that some of the differential spaces don't have enough points. And there are papers written about it. People working on differential spaces. This is called real compactness. And there were my solution would be, well, if you don't have enough points, put them in. And then you get nice C infinity schemes and you have another machine.
My question would be, like, the spaces are not all equal, right? There's some that we care about more. Like,
yeah. Right, there is a nice collection of spaces right here. And these are spaces isomorphic to closed subsets. Yeah, this is perfectly fine. And there is a characterization of the C infinity ring. So these are finitely generated and point determined C infinity rings and corresponding schemes. So you can think of the closed subsets of Rn as C infinity schemes, and then you don't have to worry about the embedding. You don't need to worry about which Rn they sit in. Oh, and I should mention that the thing that Yale and I are arguing about is you have derivations on these things. So you can think of them as vector fields. There's a notion of integral curves. Actually, on these spaces, you have perfectly nice flows. And that's easy to prove. So the flow would be a smooth map from a different differential space, and you could do it. And I guess the last thing in 15 seconds or less, C infinity differential forms pull back. So you can integrate them. Over simplices. In fact, the standard definition of differential forms in the simplex is one of these. It agrees. Not obvious, but it does. And and chains. So there's those. And I'll finish here.